Our next speaker is YuhanYao. He's currently a director at NIO. So in NIO Autonomous Driving Department, Dr. Yao, he is currently leading the autonomous driving sensors and hardware architecture team and the next-gen solution delivery team. Before joining NIO, Dr. Yao has served key roles as tech lead and system architect for Oracle, Apple, and Waymo. Dr. Yao has led efforts to deliver several industry-renowned products such as iPhone, Waymo Driver, and NIO autonomous driving systems. Dr. YuhanYao received a bachelor's degree in electrical engineering and computer science from Peking University in China and a doctorate degree in electrical engineering from the University of Southern California in the United States. So now I want to hand it over to Dr. Yao. Dr. Yao, please.
All right, thanks so much, Shuliang, for your introduction. So let me start share my screen. Hey, Shuliang, can you see that?
Yeah, I see it.
Great.
Awesome. Yes, so far, the previous three speakers, Professor Zhu, Dr. Pei, and David, they talk about contents on machine learning, on the latest sensor technology, LiDAR, and also the machine learning community and how do we evaluate our system. So I think in my talk, I'd like to share things in a slightly different perspective. I'm from NIO Autonomous Driving, and we design the autonomous driving systems and we put those on cars. Basically, by trying to leverage the greatest and latest machine learning algorithm, the sensor technology, and semiconductor technology so that we can build a very, very good electric vehicle product and to surprise the user. So hopefully I can share my perspective in the next 25 minutes. So in the first section, let me tell you more background about myself and about NIO. So what I do at NIO right now, so I'm currently leading the AD sensors and the hardware architecture department. And our mission is delivering AD functions and in the meantime, defining the electric vehicles. So by defining electric vehicles, what we really do is we define, architect the very, very powerful and state-of-the-art sensing systems, for example, the NIO Aquila super sensing systems, and also we define the powerful supercomputing systems like the NIO Atom supercomputing systems, and we integrate those two systems on electric vehicles, and we ship the product as a whole. So, and this is what we do. And let me talk a little more about my career path, because I think my transition from semiconductor to automotive as a career, from my career really echoes with the theme of this spring symposium. So at school, I was I think my major was mostly on semiconductor design. So I was studying microelectronics and electrical engineering. So the first job I took right after school is a system architect job, is a silicon architect, and I was doing the high-speed SerDes system at Oracle, or the former Sun Microsystems. And then I transitioned my role into Apple, and in which I was designing the iPhone multi-touch systems. And after a few generations of iPhone, I joined Waymo, and that's when I dived into the autonomous driving industry, and I was basically architecting the sensing systems on Waymo Driver, which is the fully L4 robotaxi. And I think 2 years ago, I eventually joined NIO, a automotive company that's doing the electric vehicles. I think that completes my transition from semiconductor to the automotive industry. And I think looking backward, like in the automotive industry, especially in the past decade, the things has been evolving really, really fast. So the cars was used to build with, the ultimate driving machine, but right now it's no longer the key point or the core advantage of the product. We're putting more silicons into the car. We're putting more compute. We're putting more advanced sensors in order to realize a very, very good experience from for example, the autonomous driving or the digital cockpit. And I think with that being said, I think I would expect that evolving really in the next decade will be even faster than what happened in the past decade. So, and I'm super excited to see how the semiconductor can enable the electric vehicles to be a better and better product in the next few in the future. And so let me share a little bit more background about NIO. Like I just mentioned, we are an electric vehicle company, and one of our key products is electric vehicles. And the vision of our company is blue sky coming. We're trying to make the transportation greener. We're trying to make the society sustainability by, enabling like the more users to be able to use the electric vehicles over the conventional vehicles. And we were founded in 2014, and we started the first use delivery in 2018. And so far, we have shipped over 300,000 electric vehicles, and that number is increasing very, very quickly. So here are the 5 models of our second generation platform, what we call that the NT 2.0 models. And we are really premium model, and we have product lines. We have the sedan, for example, the ET7 and ET5, and we have the C7, the coupe, and we also have the SUVs, ES8 and ES7. So, like about autonomous driving technology, how did we define electric vehicles so that it can be like can deliver a great autonomous driving technology to the user? And so here is some more details about the NIO Aquila super sensing systems. And we integrated different modalities of sensors on the vehicles. We have 11 high resolution and high sensitivity cameras. We have integrated 1 ultra long distance high precision LiDAR on the roof. In addition, we have millimeter wave radars and ultrasonic radars together with redundant high precision positioning units. So on the right, you can see basically some photos of our sensor coverage, of our like high resolution camera, the high resolution radar, and I think again the most iconic design of our like Aquila sensing. We put the LiDAR and 2 cameras on the top of the roof, and we make it a very, very, I think, great execution on the design side to make it beautiful. So this is the Aquila super sensing system. And here are some details about the Atom supercomputing systems. This systems is very, very important so that we have enough data bandwidth, we have enough compute to support our machine learning models, to support the AD function, and it also enables us to iterate our solutions very, very fast and also provide a redundancy to protect the safety of our end user. So we in the Atom supercomputing system, we put 4 O-rings from NVIDIA, and we are not only the most complicated solutions on the market. I think we're also the earliest. So basically, we work together with NVIDIA like very, very closely, and I think we really pushed the limit of the timeline of this O-ring product. So a little bit on the system specs. It has a super ISP pipeline that can process 6.4 billion pixels per second. And it has a very, very high bandwidth backbone network. And we have 4 SoCs so that we have a lot of flexibility to deploy our function, to iterate our function, and to provide redundancy for safety. So this is about the NIO Atom supercomputing systems. Working together with the super sensing systems, it really redefines the electric vehicles, and we are putting these systems standard on all the vehicles that we shipped from the NT 2.0 platform, which is our second generation. And in the next section, let me share a little bit more thoughts about the autonomous driving and electric vehicles, because I think they are the ultimate goal of the digital transformation in automotive industry, and I think that's why the industry is working very, very hard on the autonomous driving technology and also on electric vehicles. And so on a high level, autonomous driving is crucial for electric vehicles, and electric vehicles is also equally crucial for autonomous driving. They're really like, you cannot take them apart because they're really like tightly connected, not just from a technical perspective, but also from an experience perspective. So on the one hand, how does AD benefit from EV? So first of all, EV is a great base to integrate sensors and compute, especially the performance, the power, and the data bandwidth is increased. It has been increasing really quickly on a sensor and compute. In addition, EV has a very like responsive vehicle maneuvering capability, and it has a low end-to-end latency, which can help the function to remain safety, especially in very urgent corner cases, especially if we are driving very fast. And I think the last point is the electric vehicles, or at least one of the advantages of electric vehicles over the conventional vehicles, is that the electric vehicles nowadays is designed with advanced EE architecture so that we can maximize the software flexibility. So unlike the conventional vehicles, if you are a user of electric vehicles, for example, Tesla or other brand, the software of the vehicles can keep upgrading over the lifetime of the product, and from every major upgrade, you will have a different like experience, or you're basically realizing that your car is becoming way better over the lifetime of the product. So on the other hand, how does EV benefit from AD? First of all, it's very straightforward, right? The AD or the ADAS function can improve the driving safety. It really complements the driver, and it really improves reduces the accident rate overall. And the second, as the AD technology becomes more mature over the next few years, I think the driver, we can really free the driver from the tedious driving tasks, so that the commutes can become more enjoyable. Imagine that if one day if you drive to work, right, you don't have to focus on driving. Instead, you can focus on other great features of the vehicles. For example, the digital cockpit. Try to enjoy the content that can be like delivered from the information system more, or just simply talk to the passengers, or simply call your family. I think this is going to be the trend of AD and of the next generation electric vehicle experiences. And lastly, I think because of the AD and EV technology, the vehicle design logic will be completely revolutionized. Like I mentioned in the beginning, like previously for the conventional vehicles, like a lot of effort was put into to make it driving great. But right now, for EVs, that is very simple, like because we have very powerful the battery and very powerful electric engines. So I think in the next, the focus of the vehicle design will be mostly on experiences. How do we improve the AD technology? How do we improve the digital cockpit technology? And how do we improve the overall experience of the product? It's more than a driving machine. So the takeaway here is, overall, I think the combination of autonomous driving and electric vehicles can really create a trustable and enjoyable experiences. So, and a little bit more words on autonomous driving. So I think the point I want to make here to the audience today is autonomous driving is more than software, and it really requires a full stack specialties. So what I'm showing here is the typical and way simplified system architecture of autonomous driving systems. I think when people are talking about autonomous driving, most of the time they mean the level 1 and level 2, which is on the solution level, for example, the service, or the software level, like the perceptions, planning control, like all kinds of different like neural networks. They're important, but they're not the only thing that matters to deploy a system, reliable systems. The foundations are equally important. Like I put here on level 3 and level 4, we have the foundation on the software, like operating systems or the middleware that handles the communication of all the software blocks in level 1 and level 2. And for the level 4, we have the hardware layer in which integrated the cameras that provide the raw data, and we have the main computer provide the the computing power to deploy the software. And in addition, we will need very good connection capability so that the AD function can interact with the vehicle drive unit. I think for the semiconductor, it is a critical enabler for level 4, the hardware layer, because the requirements from the sensors, the requirement from the computings, and the requirement from the vehicles as a whole will be driving the unique requirements for the semiconductor companies, I think, in the next few decades. And that's bring us into the next section. I named that the automotive semiconductor are the critical enablers for AD and EV. And AD and EV are not, very complicated on a high level. We have to do 3 things right: the sensors, the compute, and the vehicles. If we figure out a good way to compromise among the 3, find out a good way to integrate those 3 together, we will have a great AD and EV product down the road. So about sensors. So the sensors from I think the AD sensing performance are still evolving fast because we're still trying to tackle the more challenging scenarios. And from the semiconductor perspective, the critical chips for the sensors are very important, and we will keep driving the requirements as we are trying to make progress on the AD. And nowadays, we basically use 3 modalities to support our AD function and to provide a good perception, like capability to the environment. We have the camera, and we have the LiDAR, and we have the radar, or next to the 4D imaging radar. On the camera, the CMOS sensor is really critical thing. We are trying to get the lowest, like a low noise, the high sensitivity, and high dynamic range, so that we can capture the best image to support the performance of the perception model. And for the LiDAR, like Dr. Pei just mentioned, the photonics technology, the ADC, DSP are the core of the LiDAR, so that we can keep improving the density of the point cloud, keep improving the performance of the point cloud, and so that we can also save some power and save some cost down the road. For the millimeter wave radar or the 4D imaging radar, the 2 components that are critical are: 1, the radar mimic chip, which is basically the millimeter wave transceiver that controls the antenna to both transmitting the signal and receiving the signal, and also the radar processor that conducts a lot of the radar specific like algorithms such as the FFT and other perception models that based on the point cloud detected from the radar. And the 4D imaging radar, compared with the conventional radar, it can deliver more resolution or the more number of points on the Z direction, on a height direction, and that can drastically change the way we use the radar. So, and these are some requirements from sensors from the autonomous driving system. Second, on computing. So on the left, this is a more detailed look about our NT 2.0 Atom supercomputer. We have 4 NVIDIA Orange, and we integrate them together in a very complicated architecture designed for the AD systems and designed for the vehicles. So the point I want to make here is, although I think when people look at SoCs or the AI processors, they were always asking, how many TOPS do we have? Do we have 500, 1,000, or 2,000? And the point I want to make here is that the AI SoC is not about, the TOPS are important, but the AI SoC is not all about TOPS. The chip architecture and the system co-design is very critical, so that we do not waste any silicon real estate on the chip, because in the end, this is a system on a chip. It's not just a NPU or GPU. And we need to keep more eye on the overall system architecture to make sure that we design something right and we design something that's good enough. And lastly, the requirements from the vehicles will also drive the autonomous driving semiconductor progress. And this is a comparison of the conventional vehicle architecture and the state-of-the-art software-centric architecture that are being widely developed on all of the EVs nowadays. I think the comparison is clear, right? On the left-hand side, it is a very, very like complicated network structure connected by the low-speed but reliable bus, the CAN or LIN. And for example, each individual vehicle function will have its own network node, will have its own like ECU that controls, for example, the seat controller, the instrument controller, or the AC controller, climate lighting. So this is how the vehicle were designed, right, in the past, like maybe 20, 30 years. This is good, this is very reliable, but the downside is once you define a system architecture like this, it is very, very difficult to upgrade. Basically, when you buy the moment when you buy the vehicles, it's done. All the features will be the same over the lifetime. But nowadays, especially because of the progress of the electric vehicles, we are taking a more software-centric approach. So instead of putting tens or hundreds of individual small chips, the ECUs that to handle like things like individually and separately, we now try to consolidate them into like some big blocks of clusters ECU, so that we can reduce the number of like ECUs on the vehicles. And in addition, the interconnect between all the ECUs are becoming more powerful. We are gradually ditching away the conventional CAN and LIN, and we're gradually transitioning into the Ethernet so that the bandwidth and the software flexibility can be maximized. I think I think based on my personal point of view, the trend of the vehicle E architecture will be consolidation and simplification. The reason is very, very simple. We try to get the maximum software complexity at the minimum cost. And I think that's very unique between the state-of-the-art electric vehicle architecture and the conventional architecture. So this is the last session of my talk, and the future ways of working between semiconductor and EV. I think because of all the unique requirements from the autonomous driving and electric vehicles to the semiconductor, and because that the vehicle technology will be progressing really fast in the next few decades, I really hope to discuss and work with all the semiconductor vendors to figure out what will be the better way of working, so that we can maximize the value of both the semiconductor and also the electric vehicles. For example, can OEM, Tier 1, and the silicon companies form a better collaboration mode? I think based on what I see right now, this is not as tight as I would imagine. For example, I'm raising a few questions. Basically, for example, how to define the silicon specs early and accurately, so that the silicon development cycle can be in a good alignment with the product development cycle. So that's challenging to do, and that's very, very important for the whole industry. And second, how to reduce cost and system complexity. This is equally important. How can we define more consolidated ECUs, more consolidated chips that can reduce the system complexity and to make more money out of the system? And third is because the silicon will always keep upgrading every few years. So when the silicon is being upgraded, how do we define or co-define a system architecture and make this upgrade more transparent to developers? And so we don't have to take the pain of remapping the solutions, remapping the algorithms every time we upgrade the silicon. How do we make sure that the silicon upgrades, not just from the hardware side, but also from the foundational software side, can have a good compatibility from the previous generations, so that the development will be way easier, and the go-to-market time it takes to develop the functions will be also shorter. Yeah, so I'm just raising the questions here. Hopefully we can discuss more in the panel discussions. I think that's basically concludes my talk today. And last, thank you so much for inviting me to this symposium. And I'm super excited to talk more about relevant things with all of you offline. So if you are exploring any business community, like business opportunities on the sensors or on the semiconductors, or if you are seeking for new opportunities on a career, or if you simply want to connect, feel free to reach out. I put my email, I put my LinkedIn, and I put my WeChat here. So thank you so much again for your time, and that concludes my talk. Back to you, Julian.
Thank you so much, Dr. Yao. And thanks a lot for sharing your contact information. I think after the meeting, you should definitely talk to Dr. Junpei, right? His company is, providing LiDAR sensors at a very low cost. Okay, think about that. And again, thanks a lot, for providing it's a very unique perspective from the car OEM. So if you look at the prior talks, we have perspective from academia, we have perspective from standard organization, we have perspective from sensor provider. Now we have a perspective from car OEMs. So that's very interesting. I think for the constraint of time, I will pick one of the questions, and then later you can look at the chat room and help us answer the question there. So one of the question is about basically, I think that the question is about the cockpit. So the cockpit is like, it's getting more and more interesting. And there's also a special computer for that cockpit as well. So what's your view on that? Because it seems like that one is easier to do.
Yeah, I think the logic, or the fundamental thinking like behind AD chips and cockpit chips are slightly different. Cockpit chip is more like, for example, your chips that you put into your cell phone, right? The features are iterating really, really fast. You are trying to install more apps. You're trying to enable more ways of user interacting with the vehicles. And I think that's the focus of the cockpit chips. For AD chips are slightly different, right? We need powerful, we need stable, and we need maximum complex, functional safety. And I think right now there are discussions to fuse the two functions together, like to make the single SoC solution that supports both the AD and cockpit. I think that might be one direction in the future. Yeah, but right now, currently the cockpit chips are separate from AD chips in the EV because of the way we develop things and the different requirements from the engineering perspective.
Thank you so much. I think you kind of answered the second question as well. So I will just quickly ask that follow-up question. One of the audience is asking, we have two chips, right? The cockpit and the AD, right? Is there a way to fuse them, and what are the challenges right now?
Yeah, right now there are some companies doing this, the fusion architecture, and my personal view is, I think it may start to show up in the low end solutions first, especially on L2 ADAS systems. I think that's a great starting point to try to fuse different domains together. And for the high level AD functions, I don't think we're there yet. We're still trying to figure out what the features we need, right, in AD chip. And I think for if we talk about fusing the high level AD domain with the cockpit domain, we have to wait after the AD becomes mature and we know what features we need, and I think that's when we can start to figure out how to consolidate, to simplify the system further, and to simplify and to reduce the cost further.
Okay, thank you so much. I think that makes sense. I think for the sake of time, we're going to move to the next speaker. And thanks again, Dr. Yao. And please help us answer the question in the chat.